Good.
Just got done with the second.
Okay.
Oh,
Homework. Yourself?
Still on number 4. Number 4.10 took me a second.
Okay.
I remember when I talked to you, I thought I was like, oh, they're just spherical stuff, but no, they're different. So kind of took a little bit longer.
Okay. Okay, guess we can wait one more minute. We'll talk fluid dynamics today, but we'll talk about first the equations. We'll just go over them again. And then for folks who are in computational, you'll get to see how we do it on computer fluids. And hopefully that will help you start thinking about that third problem in this homework. Homework 5. Any questions before we get started? Okay. You ever seen a picture like this before? You ever wonder what?
Like, it's kind of like topography map, but like for like weather.
Yeah. So it's kind of like a topography map. There's contours, right? Contour map. What is the H?
Pressure.
High pressure. And L is low pressure. So what would be your assumption about how the wind goes? From high to low, right? That seems fairly easy, right? You take air from here and you push it over here. That's fair? Okay. Anything that we're missing in this picture? Anything that to consider?
Those circles, is that like the height of like the clouds in that area?
These are contours of pressure.
Oh, okay. So it's not like in the topological map where it shows you like how steep or high a mountain is.
Right, so yeah, it's the same visual expression. They're called contour maps. But here what's changing is how much pressure. And what you'll notice is it's 996 something versus 1,012 of that thing. It's millibars. So these are, remember that a bar is the atmospheric pressure at sea level. So this is slightly less than the atmospheric pressure at sea level. That's exactly the atmospheric pressure, and this is slightly more. Right? And so the expectation should be that we go from high to low. If I told you that instead it goes in between these contours, you'd be a little surprised, right? That the wind follows the contours.
where people is that though? Should we not be surprised?
Well, should we be surprised? So should we expect that wind just goes like that? And it all sinks into this low? Because it's a closed system, right? So once it goes to the low, then what does it do? It doesn't disappear. It has to go somewhere else, right? It's a whole cyclic pattern. So there's up and there's down. We're missing that, of course. And also we're missing the fact that this is not just a box on the screen. This is the whole Earth. And the whole Earth is spinning. Because the whole Earth is spinning, there's going to be balances between the rotation of the Earth and these pressure forces that we're talking about. Okay, so let's have a look at what this actually looks like. Here's a different example, right? And you can see what happened here was just a little bit of time. Okay, so this is the next day, watching all these patterns evolve. And we can watch a low pressure front move across. So it's going to start up here, and it's going to move down across the Earth, the continental US. And as it does that, it's bringing cold, moist air. And it's going to bring that cold, moist air. What's it going to do when it gets to land? Okay. It's gonna create these. Clouds. Cold, moist air, okay, gets pulled in by the low pressure system. Look at the curvature here. It spins in towards the low. Okay, so here's that low pressure system. The wind is going in the direction of the contour, and it's pulling in this moisture. And as it moves in, it spins into this little object here, this low pressure zone. So we're gonna see exactly how this happens. Okay. As it slams into the continental US, it comes down in the form of rain. Okay, so usually you can tell what the weather will be in Southern California, not by looking up, but by looking at what's happening on the ocean. If there's nothing happening on the ocean, you're gonna have clear weather. Most of our rain comes from moisture coming off of the ocean, coming onto land, and then precipitating. Okay. Okay. Most of you did check-ins. If you haven't done your check-in, find your time to talk to them. Cannot pass the class without having to. This is the one that I want us to get to. Hopefully we'll get to 6.7. We'll all be able to code up some fluid. Because that's the most fun part. When you make the computer make the water, then you have a rock making a liquid. That's pretty sick, right? Okay. We're gonna try this again. You're all experts here, right? The goal is not to read the symbols, but to read the terms. Once you have said your term, you are exempt until it comes back around to the next term. Okay. So what's the first term here? Raise your hand if you have it.
I mean, density, I mean, like the relative.
So you're just reading the symbol. So what does the term mean? Are you reading the symbols? Yeah, so what's the goal for this exercise? The goal for this exercise is not just to read them. Okay? It's to know what they mean at sight. Right? It's not just sounding out the letters, it's knowing what the word means. Does that make sense? So we're taking a step above what we normally do. So at the beginning of every class, until we have this nailed down, we're going to be able to point here and say this term does blank. It's not just the rate of change of density with time. Okay, I can spell out the letters and I can make that sense. We need a meaning. Because we're not just thinking about the math, we're thinking about the concepts behind the math. This is a language. This is a statement. This is a whole paragraph of text consolidated by mathematics. So what does this first term mean? Yeah.
Total. I want to say total change of density in the system.
You're almost there. If I did this, you'd be right. This is the total change. Oh God. Right? And it's comprised of what two components? This is the steady part of the density. How is it changing or not changing with time is the interpretation. It is thinking about the rate of change of the density. So we would call it the steady part of the density. Okay, what's the second one? Not trending.
That's how everything's moving.
Right? And that has a special word. Well, it is the right thought, but it's not the word that I need. Each one of these terms has a name. That's the effective. Okay, so that's a half point for both. Okay. Okay. And what's the top equation? What the whole thing means? Mass is conserved. Why do I know that mass is conserved? There are no sources or sinks of mass. Mass is not generated nor destroyed. Is momentum generated or destroyed? Yes. Good. How has it done that?
Uh,
Give me a term.
friction would stop those forces.
Yeah, which term?
It would be, I think it's the second one, rho G J,
What's this one?
body forces.
Body forces. Okay. Are body forces friction? No. What are the body forces?
What it feels from gravity.
Gravity, right? Gravity works on the whole body, on the whole jelly bean. Good. Okay. So that was,
Right, I think I found the one with friction.
I know, you got yours, okay. Yeah. Which one? This one? Or this one? This one?
It has to do with shear forces.
Here, term 3? Yeah, what does this have to do with?
Due to shear forces.
Shear force, that's really the word I wanted to hear, right? And we can see that in the directionality of the derivatives. The J and the I, right, they're opposed. Right, when they're in the same direction, those are called when they're in the same direction, they're called what? There you go. Compressive forces, right? So these are compressive forces. And we see that here in the M, the dual M. Good, we have 2 more terms, so we can recycle now everyone's gone once. What are those first 2 terms?
First, negative dT is the pressure force.
Very good. Pressure forces. See how we're not just reading them, we're kind of understanding them a little bit. It's not the derivative, right? It's like what it actually is, the pressure force. Good, and what's the last term here? Conservation of momentum, yeah. That would be the whole statement, right? What's the name of the equation? You know the name of the equation? Anyone? Every stocks. Okay. The first term you might call the total derivative of the momentum. That would be okay too. Right? So the first statement says this is the total derivative of the mass, and that is 0. Here's the total derivative of the momentum, and it's due to all of these sinks sources. Right? Each one of these can produce or remove momentum. Good? Okay, let's do the next one unless there's any questions here. No fun pictures. Alright, what's the next equation I'm gonna show you?
Observation.
Conservation of energy, good, that's a very natural way to go. Um. What are the things that we're gonna consider in the conservation of energy equation?
Finding for-
Good. Good. What generates energy of those types? Works, who does the works? We do. What do you mean by we do? What's that? Sure, but there's two types of workforces, like things that, for example, we saw here, we have. Body forces, there's shears, there's compressions. Do those have analogs in energy? Work done by pressure, right? What would that be called? Remember that term? So this is the full energy equation. There's all types of terms here. And chances are you're gonna get them wrong at the beginning. This is why we do it at the beginning of every class. You get better at it. Left-hand side, you already said it. What is that thing on the left-hand side?
Total conservation of energy. Turn on energy.
Yeah, so this is a little dumb, right? This is the total derivative of the total energy. Okay, so how is the whole thing internal and kinetic changing? And then on the right hand side is all the sources and sinks. Okay. So what are the sources and sinks that you see and you're very confident in? Everyone but Trin.
I know the last one is heat.
Last one's heat. All right, got that one. Easy money. Good. All right, everyone but Trinity and Kevin. Another Trin. But what do you mean by that? Let's use more words than just gravity here. Help me understand what this term is, does. Excuse me?
The body.
The body force work, right? In this context, done by gravity. So this is the work done by gravity. Where?
The work done by the surface.
Work done by a surface? You want this whole thing?
No. Just.
This piece?
Yeah.
This one you want is work done by surface. Okay, surface forces. Okay, we like that? Pressure and viscosity? Pressure and viscosity?
Has to do with, stresses, right?
This one has to do with stretches, but also this one, right? So this is where we tend to get it gets a little tricky, right? Because the exact ordering of the letters now matters. Okay? So usually what I like to do here, and we're not gonna do it for every single one, but I'm gonna do it for you right now, is we're gonna break this apart like we did a couple weeks or a couple of classes ago. And I'm gonna show you where each of the pieces go. This E, you see the arrow starts and then it becomes really dark. Sorry about that. So this is the total energy derivative. And it's a result of these three terms. Let's see if we can trace them back to their sources. This first one comes from where? Let's go to the third one. The third one comes from where? What? The heat transfer, right? This just comes right down from here. Let's see if I did this properly. Don't look. This one came from here. Okay, this is that third term, and we divided by rho to put it on this side. Okay. This thing here is what? What is this little V-ish thing? Not velocity, it's volume, specific volume, right? So this looks like what term? PDV. That's what you should see. You should see the letters PDV. And PDV is a type of work, right? We do PDV work whether or not we're moving a gas or a liquid, right? As we change the volume, we can increase the internal energy here, right? Okay, so this is like compression, expansion of the gas. You change the volume, the internal energy changes. Okay, so what's this thing here? There's definitely a strain rate tensor in here, right? And there's some other stuff in here. What does the term mean? So these are all changes to the internal energy, right? And this term up here, PDU, became PDV because we divided by the volume or by the density, right? Okay, so that's fine. This thing here, you know where it comes from? Yeah, there's the viscosity right there. That's tau. And then we see Sij is the definition of this thing. We calculated Sij for homework 3. You'll see that that's the same thing. So it's Tij, Sij. Right? So what does it mean? There's 3 ways to create heat in a fluid. We talked about putting heat in it. Great. That's one way to create heat. We can change the volume. We can expand or compress the gas or fluid, right? Or we can transfer it by moving it around. Yeah, so this requires viscosity, right? This is called viscous heating. So what we're doing here is we're taking bulk flow and we're converting it into internal energy. Does that make sense? What's the example of that? Rain?
I said rain.
Rain, no. Okay, so as I keep my hands like this, what's happening is there's a layer of oil in my hand that is moving very quickly. As it begins to move quickly, there are viscous forces, right? And those viscous forces take the energy that should be linear, moving each of those molecules, and turn them into heat. My body cannot sense flowing water. Maybe it can, based on like different pores. But the idea being that you can sense heat very, you have a lot of heat receptors, right? Do we get all these terms here? Okay, so this term, total change of internal energy, is due to the PDV work, is due to viscous heating, and is due to heat generation. Okay, go to the next one. What's this on the left-hand side? Good, total kinetic energy. This is how we change the total kinetic energy. And what are the modes that we have to do that? How do we generate kinetic energy? Use gravity or body forces. So we have a body force term. We started off the class thinking about this. Highs and lows of pressures. So this is your pressure term. These are pressure forces. High pressures push stuff to low pressures. Right? In this term? Good, but it's a specific type of friction. We think of friction as dissipative, right? Usually when we think about it, we think about the motion ending. This is unique type of friction. This is the type of friction that you can splash your cousin with. Shearing force. Okay, so let's try this again. We're gonna work on this together, okay? Over here is the change in the internal energy. The change internal energy. Now why? Oh, fuck, I spelled that wrong. Whatever. What's the first term? PDV work. PDV work. Another way of thinking about that is good.
Okay.
Like pressure.
Yeah, this hand motion is right. Compression, expansion, right? Good. What's the second term? Viscous heating. Good. What's the third term? Heat flux, heat generation, direct heat. We're gonna do heat flux today. Good, and what's over here? Good. And what's the first term? Good. Second term? Pressure forces? Third term? Okay. So let's put it all together. In order to generate kinetic energy, I can do it in three ways. I can apply a body force. I can apply a pressure force, and I can apply a shearing force. That's how I create kinetic energy. Okay? Or take it away. In order to generate internal energy, in order to change the temperature of the gas, so to speak, right? I can do PDV work, I can do viscous work, and I can add heat to Q, the heat flow. Okay? We see how these are not just math, right? It's real statements. It's telling you a paragraph about how energy is generated in the fluid. We just do it with a line. Wednesday, we're going to be very good at this, right? Faster, even better. Okay. Because next Monday, you're going to get an equation each. You have to do the whole equation yourself. Okay. All right. How many folks have taken 3300? Physics 3300? One. Arts. No, computational. Oh. Well, you're in it. I know you guys are in it. You're in it. Yeah, but you're not. Okay, so it's, did you finish?
Yeah, that's what's true.
Yeah, so it's two of you have finished. Four of you have not.
Are they gonna show us?
I guess so, yeah.
Just let the-
Yeah.
Yeah, I tried it, that was coming.
Yeah, well, it's hard because I haven't shown you the material yet. So, we're gonna talk just really briefly about computational fluid flows. And the reason why we have to talk about them is because, we just showed you how complicated the mathematics is, right? And generally speaking, there are certainly applications in which we can create assumptions, and we will do that for a lot of the semester. We'll talk about all the simplifying assumptions that we can use. But for most fluid problems, you need a computer, right? And computers are nice because all you have to do is just define the region. As long as it's not infinite space, you should be able to simulate. So for example, let's take this as some channel, some like pipe that comes in, and then the pipe gets wider. So this is some boundary. To show the boundary here is curved. And you might want to know how the flow changes from when it enters to how it is out here. Right? So generally speaking, this is quite solvable. It's two-dimensional, it's in a pipe. You can prescribe specific things about the flow, and then you assume that it's in steady state. You let it run, it'll come to some relaxed configuration, and then it will look like that forever. Okay. So we can let computers do the work for a majority of the more complicated problems. You can even do fluids in an infinite space. You just have to be a little careful. We'll talk about that later. If you're really interested in fluids, for example, like how the interiors of stars behave or how the flow on a planet works, you have to be able to solve all of these things on a computer. What does the word finite difference mean? I think everyone should know this word, right? Okay, I like that. It's an interesting idea, right? Because it's thinking about like integer difference, finite, like countable. This is an approximation to a derivative. If I knew where the hell my chocolate. Oh, here it is. No, that's not it. Here it is. Okay. So this is the derivative, right? What's the definition of the derivative, by the way? Good, it's a limit. So we say something like dx or dd f of x is the limit of
X approaches something.
x approaches something or h approaches what? X. Definition of the derivative, folks. This is the basis of your whole career. Definitely don't have to memorize. Zero, good, okay, so h goes to zero as what occurs? Some functions, what?
X plus H.
Okay, so this is what Isaac Newton is famous for. Okay, regardless of whether or not he found it out. So this is saying that we can construct this thing called the derivative. And, it's kind of like an imaginary object, right? Because h going to zero, well, we all know that 1 over 0, that's not defined. And yet, f of x plus h minus f of x, as h becomes smaller and smaller, you would expect that also to go to 0. And we know, of course, that as those both things head towards 0, their ratio head towards a constant, a real value, right? So it just so happens that we can construct this seemingly figment of our imagination has a real meaning. What's the real meaning of the derivative? The slope. So it has a true understandable thing, which is the slope of the function. But in practice, we as human beings cannot take infinite derivatives, right? We can't get infinite precision. And especially can't do that on a computer. So instead, we do something called the finite difference. How do we write the finite difference?
That's it. X plus H.
So I'm gonna put a little tilde, says approximately equal to f of x plus h.
Obviously, that's-
Yeah, that would be a version of the difference, right? That would be a central difference. But this is just a finite. Any of them will work. This would be an example of something called a forward difference. Of course, as Trinity just mentioned, there is something like a central difference and a backwards difference. Okay, they're all approximations of the derivative. Okay. What does finite volume mean? Anyone ever heard that saying? Okay, so if you go to chapter 6 in your book, this is computational fluid flow. And there's only one chapter in the book. I mean, there's like, I don't know, 20 chapters, 15 chapters in the whole book. And they only really put aside one for computational fluid flow. Because really you need your own book on computational fluid flow. We're just going to talk really briefly about some of the easiest things to do. So, for a finite volume, what you do is you control the variables within the volume, as opposed to following the individual grid points. And what I mean by that is, just like we saw earlier in the semester, we talked about the difference between Lagrangian and Eulerian flow. That is, are we moving with the flow versus are we staying at a fixed point and watching the flow go by? Right? The finite difference method does the latter. We take grid points at every location, and we ask how the flow moves along those grid points, as opposed to finite volume, which watches how the flow evolves from the perspective of the flow. It's two different ways of writing the same mathematics. We're going to mostly stick to this first one, the easiest to code. You can do finite volume, there's fun approximations if you want to do that, and we'll talk about like vorticity flows in a little while, doing stream functions, for example. Okay. So we can look at finite difference, and you can look at an image like this, and you could say, okay, so if I build my simulation, I know how to make an array, right? So I can just ask for every part of the array, I can ask it to do derivatives. So for example, let's take this point here. If I want to know the flow, I can look, for example, at the pieces around it. Up and down, left and right, up and down would be my derivatives with respect to y. Left and right would be my derivatives with respect to x. And if this evolves in time, I might be updating this, right? So I'd have an old version and a new version, and then my derivatives would be in this direction, out or in of the board. Those would be with respect to time, right? Make sense? Yes, no, maybe so. All right. Let's learn the first set of rules for coding. Okay. So let's think about this flow that is basically just moving, okay, and is able to take any quantity that I might be interested in, whether that's heat, something else, and allow it to diffuse. So what happens to something when it's very sharply concentrated? Let's say you take a giant block of salt, you drop it into water. What happens to that salt? What was that hand motions? Yeah, it dissolves and also gets diffused out, right? The natural motion of the fluid is going to take that salt and it's going to redistribute it until all of the concentration in the entire fluid is the same. That is the act of diffusion, right? So generally speaking, you might have two different things. Let's say this is some parameter f, okay, at some time t1, and has some concentration, maybe some peak value, but maybe you're also moving. So the flow is being advected, and you notice that the peak maybe moves a little bit, right? Widens. So that could be the diffusion, right? Very good. Okay, so let's do a bunch of math. Let's start with thinking about our control volume. So let's think about some jelly bean following in the fluid. Okay. And we say that the rate of change of the jelly bean, ddt, over some boundary dx of some quantity f. Is that fair? Let's think about this maybe only in one direction, but only in change in x. Okay. So how is this thing changing? Well, it's just going to be the difference between what you started with and what you ended with. You agree with that?
What is the dollar line?
This is f at some later time. P plus t delta t. So we start with some function f, doesn't matter what it is. We're just thinking about how it diffuses and advects. Okay. And so we start with this parameter f, which is the sum curve. Okay. And then we watch how it's changing through some delta in space, some change, some little space difference, right? How does it move through there? Okay. If you were thinking about this as the jelly bean, this would be how does it flow through the jelly bean? But this is a one-dimensional jelly bean. This is essentially a line. And what we're asking for is how much stuff of this line moves through this region. So you could say, this is what you start with, right? This amount. This is what you end with. And what you want is the difference. Does that make sense? Okay. So this allows us to construct something like an average. So f average is 1 over delta x integral delta x f of x dx. And similarly, if we took a derivative of this, we could get back to here. So we say d dt of f average. That would just be 1 over delta x, because the derivative of this thing is just these two, times f in minus f out. So this is the start, this is the finite volume method. This is looking through a specific amount of space and watching how stuff changes. Okay? So if we wanted to know how this property, ADT, of this thing is, on the average value, how is that changing with time? Then I only have to consider some part of space and keep updating what goes in and what goes out. That's sort of how we thought about the jelly bean in the first place, right? How do we move the jelly bean around? How do we put stuff in or out? Well, you just got to keep track of that surface. Now, on a computer, that's much easier than it was to do with integrals, right? Because if you have an integral, then by hand you have to do it, and those fucking suck. But for a computer, you just ask, okay, what was the value at the beginning of the simulation? And then what was the value at the beginning plus h, plus 2h, plus 3h, so on and so forth. Let time run forward, and you can do these finite volumes, right? Okay. All right, let's try it one more way. So we can keep writing this. We can rewrite this one as the let's see how do I want to write this? Let me pull this up. Okay. So we can take the integral of the derivative of f. Now remember that I'm saying these things because we're keeping in mind the fundamental theorem of calculus, right? About the differentiability and integrals being inverse processes of one another. Okay. So we can say that the integral of the derivative of f is equal to the difference of the values of the endpoints. You remember that part? Okay. So we could say something like f out minus f in is equal to the integral delta x delta f delta x dx. That's not witchcraft, right? That's just the definition. Fundamental theorem of calculus. Okay. So now we have something over there. We have something over here. We have something over here. We have some ddx's. So I'm going to go ahead and write this as d dt. The integral delta x f dx. See that comes from over there? And that's going to be equal to minus the integral of df dx dx. Also over this location. Okay. Any questions so far? Are you confused at all by the F's? Do you remember from the picture that one of them is the little f, and the little f, the big F is evaluated at a point? You okay with that? Big F, evaluation of little f. Okay. All right, well, let's move these over. We've played this game before, right? We move the delta x's or the integrals over delta x to one side. They both equal 0. That means what about the integral itself? What's that? That also has to equal 0 identically, right? So therefore the interiors must be 0. So let's do that. Let's do delta x. So now we have something like d, and I'm going to be a little careful here. Let's see, partial f partial t plus, I move that over, partial f partial x dx equals 0. So then this thing has to be 0. Identically. Right? Okay, so before we can go ahead and solve this, we have to specify our fluxes. Okay. And so we can do something like we can define F as advecting the flow. And we can just write it as the flow times whatever function that we're thinking about. Okay. The diffusive fluxes, they're a little different. So this is the advective fluxes. Say that with an A. The diffusive fluxes with a D, I'm going to write as minus D, which is the diffusive constant. And then also I'm going to write this as df dx. So this is how the shape is changing. So if there's no curvature, then there's no diffusion. It's constant everywhere, you don't have diffusion. It's sharply peaked, you have more diffusion, right? So we can now add these into here. And we get something really beautiful. We get df dt plus u, now this is the flow, df dx is equal to d del squared f del x squared. Okay. What do I say? Because you kind of recognize it, right? Yeah, steady advective something about f, right? There's a steady term. There's an advective term here. And then what's this? I used a D, but it's a different D.
Acceleration.
Okay.
As a total.
Okay, so it's actually just one word, it's just the diffusive part. Okay. So if something is sharply curved, this is speaking about the curvature, this is going to give us how much diffusion we have. And diffusion usually looks like this. Some constant times the second derivative of the function. So if I wanted to, I could move this to the other side. And I could do that function. That. Okay. So how would I interpret that? I would say that F, some property of the fluid, is decreased in time when stuff flows away. When this is positive, this term flowing decreases it. Or this is positive when stuff diffuses into it. Does that make sense? This is the simplest thing you can code. And in fact, you can solve it analytically. How do you solve it analytically?
You have to find like a general solution that satisfies that, right?
Yeah.
Would you? I think integrate with respect to C on both sides,
I hate that. Why do I hate that?
because it's hard.
No, because we don't integrate in this class.
Oh, okay, but is it right?
No.
Okay, gotcha.
No, we hate integrals.
Gotcha.
The point of homework 2, the point of the third problem of homework 2 is to get out of our mind that integrating is an option. Adults don't integrate. Tell yourself that at home. Okay? Integrals are for when it's simple. Integrals are for when you can understand it, quite easily, analytically. And they're helpful. They put us in the right direction. But generally, these systems get so complicated that we don't want to rely on them. Because you're going to go down, you're going to have error functions, you're going to have all sorts of weird integrals that don't make any sense. But if we do just a little bit of guessing, we will be more confident in our answer. So we're going to guess the solution.
Thinking trig, because it's the second derivative is the same. either
Okay, you're saying the word trig, but what do you mean by that?
Like cosine or something.
Okay, so that's different than trig, right? Okay, so we would say we're gonna guess a periodic solution. Okay? Now, the reason for that is because, as Trinity pointed out, the second derivative is the function. Okay. So we might look at this and we say, well, there's two spatial derivatives and one time derivative. Okay? So we might say something like f, that could be some function of time and some function of space. Ever seen that done before? No? Okay. So this is called separation of variables. What we do here is we assume that they're not mixed together. So it's not x plus t inside of, say, a cosine. Now this might be a bad assumption. We'll find out when we do it, right? So you could do it this way. This separation of variables would allow you to say, well, this is a cosine and this is a sine. And then you know how sines and cosines can be added together trigonometrically, right? The laws of sines and cosines. Okay. So you know that this one here would become something, this one here would become something, and you would have some little terms, and all you have to do is go through the process of writing them all down. Or you could already know how it goes, and you could assume a solution of a particular type. You could say, this piece here is going to act diffusively. So I'm going to give it a diffusive shape. Oops. Why is that a diffusive shape? Yeah, so this thing is decreasing exponentially with time, right? K squared, we haven't really defined that. That's one of the constants that we'll see. D is our diffusive constant. So essentially what we're going to see is that this thing works to smooth everything out. Okay? If you didn't have any flow at all, you only had diffusion, then you'd only have this term, and that term would be a natural solution. So let's say we drop this entirely. Okay? Then you would have something here, two derivatives with respect to space, gives you something with respect to time, and that's the solution. That's the solution to the diffusion equation. Okay? Similarly, if you have an advective term, you have one derivative with respect to time, one derivative with respect to space, and you guess a periodic solution, that's perfectly okay. You could say sine or cosine, I don't really care. And you can imagine it's a wave. Let's say that it's going to the right. You might do something like kx minus omega. Right? That's a perfectly good guess. You need to adjust it slightly, right? You'd have to go in here. You'd actually have to find out what these letters are. And there's something like 2 pi 2 pi k x minus big UT. What does that end up looking like? It starts off as a sine wave, maybe moving to the left, but it diffuses. So some property of the fluid is moving to the left, but getting smaller and spreading out, or getting less tall and spreading out as it goes. That is the process of advection and diffusion together.
Would that look like when we learned in classical, like a damped oscillator, right?
Yeah, this thing, right? Yeah. Gonna damp the motion. Yeah.
What's next to the two? Is that supposed to be?
Yes.
Where? Oh, this one, yeah. Just a little baby H. Okay? Okay, so that was finite volume. Let's do finite difference really quick. Do you know your finite differences already? You know where to find them? What? Yeah. Yeah. You know how to write your finite differences for x and t's and whatnot? Because let's convert this equation into finite difference. Yeah.
You rewrite that using the definition of, derivative?
Right, I want to rewrite it with the finite difference.
Okay.
So how would I do that?
You do that whole thing in parentheses and put plus h with it. Because we're putting it in the formula. So like that, parentheses and plus h and then parentheses again.
This?
Yeah,
Okay, let's do some rules first. We're maybe saying the same thing, but let's just make sure. ddt of f is what? F of t plus h minus f of t over h. Is that what you meant? So this would go here. What goes here? Okay. What about the second one? B dx squared. There is h squared on the bottom, but it's not the same thing on the top. No, because remember, it's not the derivative squared, it's the second derivative. Second derivative doesn't tell you the slope, it tells you the curvature. So how many points do we need to find curvature? What? 2 gives you slope. Rise over run. Right? So 3 gives you curve. Right? Because if I do this, it's curved up. If I do that, it's curved down. Up, down, up, down. 2 can't give you up, down. It can only give you slope. So instead, I write here for the second derivative, f of t, or maybe I'll do this different. Let's do f of x plus delta x. Is that okay? Minus 2 times f of x plus f of x minus delta x. And on the bottom, x squared. Fair? Is this easy to code or hard to code? No. This is the easiest that it gets to code. Okay. Now, what I mean by that is that we can take some box. Okay. Every point of that box is a point in the array. Okay. So in order to solve this, we want to solve this thing here. Right? We can convert this piece into the future. Okay. So on the left-hand side, you have your time getting updated. On your right-hand side, you have y. That is, why is it occurring? if you have your RK4 simulation, then these would be your derivatives, right? And they depend only on the fluid properties at that exact location and time. So take this one here, df dx. I look here, right? And I'm just adding or subtracting values here, right? So whether I choose to do forward difference, central difference, backwards difference, that's perfectly okay. I'm just using the stuff along X. If I want to do it in 2D, I then need to grab this one and this one as well, right? And then what I'm doing is between each successive time, I'm updating the array. And I'm watching the fluid develop time step by time step. Okay. If we hate this, then on Wednesday we can like do it in person on front of a computer. I remember we did that last time. People like that. Yeah.
So how many time steps would we plug into or like have it go to?
And I mean, it's your experiment, right? Once you have the flow flowing, does it stay flowing? Does it break down? Right? Questions, comments, concerns? Okay. On page 236, you will see a solution. Right there. So that's not in Python. I forget what language it's in. Is it Fortran? No, it's a disgusting language. Don't use it. But it does show you how to code this up. And most importantly, let's see if he has the solution. No, I don't have the solution here. So you saw that we had this example, right? And if we guess the solution, we can put those values into a computer and we can watch time evolve just by taking t, letting it move forward. So you'll watch a sine wave sort of get smaller. And you can see here on the left-hand side, that's the exact result in dark. Here on the left-hand side, a very useless book because it's only the thickness of the lines, and this book does not come in color for this figure. I don't know what the fuck they were thinking, just do a dotted line and a non-dotted line. That would be much easier to see. But you can see that the exact solution and the numerical solution, the one that they simulate, they're quite close, right? And by the time that you ramp up the number of boxes, then you get a very good approximation. Now, we often talk about in computational the importance of taking a small enough time step, and of course, the importance of making a small enough grid. With fluids, this is even more important. These are nonlinear phenomena, which means that they depend on particles very nearby or boxes very nearby, and they depend on them not just linearly, non-linearly, so sometimes u squared times the derivative of u, right? What this means is that if you don't take a small enough grid size, you're going to miss the physics, the whole fluid will be wrong, right? So you generally will need to adjust your h's to be very small, and your distance between boxes very small until you see the fluid flow not changing with grid scaling, right? So, excuse me, just like we do in math, computational, you decrease h, you keep decreasing h until there's no difference in the output, and then you stop. Right? If you're seeing changes because of the grid size, you haven't captured. Okay. You can write the finite volume equation. I do not require you to know it. I think if you just know finite difference, that's fine. You may find that instead of doing forward difference methods, which are implicit, they require information in order to move forward. You can use explicit schemes. So if you go to page 243, they talk about what's called a leapfrog scheme. And this uses time as a spatial derivative. What this means is that you know a little bit about what happened and you know about what's going to happen. And so you're moving back and forth. So you, instead of going from time 1 to time 2 to time 3, you go from time 1 to time 3 to time 2 to time 4 to time 3, time 5, right? This is how you jump around in the grid. And what this does is it really actually helps to blend time with space in a way that's very reassuring for the computer, right? Because you're going back and you're correcting the material. So you can see that. We'll talk in a lot more detail about stuff that is called like boundary value problems. But I really want to introduce the idea of using the computer early, because then when we go to code up simple solutions, right? Like this thing here, that doesn't look simple to you, right? This looks complicated and you could not guess the answer, right? That's not something that you just instinctually know. But by the end of the semester, you will be able to guess them. And you'll realize this was the easiest one we could have done, right? And later ones will be worse. But if you can code the easiest one, then you can start to code the harder ones, right? And you don't have to know the solution to start with. Because if your code works for this, and you can validate it with an actual function, one that you can see and compare it to, then when you apply it to the same piece of code, when you apply it to things that you can't solve analytically, you can be confident in the results, right? So that's kind of where kind of diverged a little bit from the book. We'll come back in thinking about the special examples soon. Let's see if we can look at the rest of the semester really quickly.
The common problem for this week. On paper.
You don't. No, you don't. Definitely do not. Please do not send me a paper cutout or a paper screenshot of your code. Send me the code. So do your first effort at the code. And see, this is where we just were. We're only a week behind. That's fucking Gucci, right? So we'll do it here. This is supposed to be here. That would be today. Actually, we're not even a week behind. We're only 1 day behind. Okay, so on Monday, on Wednesday, we will just bring our computers and we'll just do code together, like friends. Okay, specifically like friends. Okay, and then we'll make rocks do what? Cool, right? The goal for the class is you should be able to boil water. And I'm not talking about making soup. Okay. You want your rocks to boil water, and that is incredibly hard. So just think about all of the things that we use computational fluid modeling for, whether that's aerodynamics, whether that's for, understanding the interior stars or weather modeling, right? It all starts with this very beginning, which is getting the fluids to behave. Okay, so once we do that, we're going to go into something called vorticity dynamics. And we're going to use the vorticity of the flow in order to reduce variables. We're going to get into something called gravity waves. These are special solutions to the Navier-Stokes equation. We'll look at waves and density interfaces. That is to say, watching how the interface between, say, water and air, how do those behave? We'll look at internal waves. How do waves propagate as a function of height within the medium? So you've seen ocean waves. You've ever wondered why they break? Okay, that's what you would find out here. You look at non-inertial reference frames. So this is the first time that we're going to look at the Earth spinning. You'll notice that it's the end of chapter 4. So if you want to read that now, it's basically just going to teach you about the Coriolis force, about the centrifugal force. But these all tend to go together because vorticity in a rotating frame, and these are all necessary in order to understand geophysical flow. Because that's where we're headed. We want to move towards understanding how flows on the entire planet work. So things like geophysical flow, how do we go about turning the Navier-Stokes equation from something that is a beast into something that we can break down and use the important parts of? So not every piece of the Navier-Stokes equation is applicable in every context. And how do you, as a professional, walk in and say, here we can ignore the steady term? What do you need to have in your bag in order to do that? So similarly, we'll think about geostrophic flows, and that's going to go back to the image at the beginning of the day. Geostrophic flow, geo meaning of the earth. I'll let you figure out what strophic is. So at home, what we call homework. Okay. Laminar, you've heard that word before? What does that mean? Looks like it's not moving. Yeah, that's a correct description of laminar. But do we know what the word laminar means? Or where it comes from? Have you ever heard it for anything else? Laminated paper, good. Lamination is
Flattened surface.
close. Layers. Okay. So we'll talk about laminar flow. We'll talk about some exact solutions. So there are some exact solutions to the Navier-Stokes equation. This will not get you $1 million, already written into a textbook, because they're not general solutions. They're just exact solutions. We'll talk about similarity solutions. This is really cool. This is a really powerful view of fluid dynamics. What it says is that scales don't matter as long as all things are equal. And what I mean by that is we don't need to simulate a plane at full size in order to understand aerodynamics. If we can shrink the plane down and likewise do other things to it, the fluid will behave exactly as though the plane will at much larger scales. Right? So the air tunnels that you see, we don't stick a Boeing 747 in them. And yet we have very good models for how the air flows. And that's because of similarity solutions. Right? It looks the same going down. Here, and this is when I really start to like the class, these are boundary layers. So this is the intermolecular, like going between the fact that you have a hard surface and a flow, and how do you connect those two types of physics? And it's fun. This is when you can really do very interesting problems, because this is also combining with these ones here. This talks about stuff like how does wind, for example, pick up dirt? That's right here. Go a little bit farther. Okay. We're going to talk about Ekman layers. These are in the water. They go down into the water. There's a lot of dynamics in the ocean you maybe never thought about. They're cool. We have different types of geologic waves, or not geologic, geophysical waves. These include things like Kelvin waves, internal waves, and Rossby waves. These are planetary scale waves and tides. We'll talk about instability. And then we have a lot of slide. And that's usually because I won't get through this that quickly, okay? And you'll have troubles, and some days it'll be easier, some days it'll be harder. So if there's something that you see in the textbook, if you're thinking about what you want to do for your career, and you're like, that's not covered here, right? My job is to get you to here, to get you to the Navier-Stokes equation. And from there, we're allowed to do whatever we want. So if we want to adjust some of the expectations, if you want to learn less about the earth and more about a pipe, just tell me, and we can focus more on one thing than the other. Okay. Questions, comments, concerns? Okay, break.
Check it out.